Hello, hello. Good morning, everybody. It's unclear. Can people hear me? Somebody give me a yes, chat. Yes, excellent. Let me pause this. I'm going to give people a second or two to join us. Today I'm going to be lecturing from the cockpit of the Millennium Falcon. All right, mute everybody.
Not gonna lie, I'm kind of jealous.
Let me see, manage participants. Well, if that gets you jealous, hold on, let me show you what I just built. Dun, 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 dun. Oh, you can't see it. So I don't know how well you can see it, but I spent quite a bit of time building the Lego Millennium Falcon.
Oh yeah, it's pretty awesome.
1,351 pieces. I bought it to do with my daughter and I, and then I did it myself. Okay, so a couple things. Everybody took the celebration, which is awesome. Didn't have to track anybody down. I believe you should be able to get your grades now. I will post the solutions, but the average for the class was a 79.1, and nobody took more than about 2 hours to do it. So it seems like, yeah, people did fairly well. And the other thing, as long as you're practicing social distancing, a couple people have asked me about grades. I will try and calculate your total standing next week and give it out. So I will give you quiz average, homework average, celebration average, PLCs, class participation, and all of that, and just let you know how you're doing. And then just sort of let people know also if I'm going to end up curving the final grades and stuff like that. Right now, it looks like people are doing fairly well, but you know, at the end of the semester, I want people to do well. So not going to have the exact 900.
Here.
Let me mute all for a second. Okay, actually, before I jump into looking at the cross product, any questions that people have just about anything? Just open it up for a minute or two to see if anybody has any questions. If not, so just so you know, we have 3 weeks left in the semester. Chapter 12 is a big, giant chapter that I usually spend like 2 weeks on. Probably going to cut down on some of the material, but we're going to cover chapter 12. And then we kind of had 3 chapters left that I was going to pick and choose from. So I'm going to sort of decide what from chapters 15, 16, and 17 we're going to cover. So I'll sort of let you know that. But we're going to do chapter 12. In terms of next week, I think the only thing that's going to be due is you have a lab, if you haven't uploaded lab 9 yet, or lab 10, whichever one was the last one. And then PLC, I have to figure something else. I think I might just give you guys a week off of the PLC, even though I'm not supposed to, or have you do something nominally. Okay, so what I want to do is, rather than jump into chapter 12, one of the things when we were covering vectors, you know, I didn't really go into dot product way back when, because we didn't need it until we got to work. I didn't go into cross product either because we weren't going to need it until we got to torque. Now that we're getting to chapter 12, we're going to start looking at rotational motion. So cross product is going to come in. So what I want to do is give you a little review of cross product and teach you a little bit of matrices if you haven't done that already. So I'm going to share this screen with you. Just as a little reminder, I'm pretty psyched. I got a new little Wacom tablet that's wireless Bluetooth, so hopefully I can do all this. So let me just remind you that the dot product or the scalar product. Remember, if I had 2 vectors, and let's say vector A was pointing to the right, Vector B was up at some angle, and let's just call the angle between them theta. Your book uses different angles. It doesn't matter what we use. Just the angle between the two vectors we're going to call theta. Remember, the end result of the dot product, the way it's defined is, it is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And the big thing about this is the result of this is a scalar. It's just a number plus units. And if we're given the x, y, and z components, I can get the dot product as ax, bx plus ay, by plus az, bz. We ended up needing the dot product because the work for a constant force was defined as the dot product of the force into the displacement. Well, now we're going to start looking at what's called the cross product, or the vector product. And the big thing about this is it is going to be a vector, which means the cross product has both a magnitude and a direction. And the direction that we use to figure out the direction of the cross product, we're going to use something called the right-hand rule. And let me just throw this out here. You are going to have about 3 or 4 different right-hand rules once you get to physics 4B. And the reason is because, well, I won't go into it, but magnetism is a very interesting force. And the magnetic force on a moving charge, you have to determine using the cross product. So 1, how do you define the magnitude of a cross product? So 1, the magnitude of A cross B. So 1, the magnitude of the dot product was the magnitude of one vector times the magnitude of the second vector times the cosine of the angle between them. In this case, for the cross product, it is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. So dot product is just a scalar, and the end result is a number plus units. And in terms of vectors, it's the magnitude of one times the magnitude of the second times the cosine of the angle between them. For the cross product, the magnitude is given by the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. That gives the magnitude. Now the direction is the part that's a little bit trickier. So the direction is given by the right-hand rule, which we write as RHR. There's different forms of the right-hand rule. I'm going to teach you the one that I think is just most straightforward. So 1, let me just preface this by saying the direction of the cross product or the vector product is always perpendicular to the plane containing both vectors, and you just need to determine which direction it is in terms of being perpendicular to the plane. So for example, if you look down here, here is vector A, here is vector B. The plane containing A and B is shown in gray here. The cross product, the direction is always going to be perpendicular to both vectors. So in this case, if my plane is horizontal like this, there's only 2 choices for the direction of the cross product. It's either perpendicular straight up or perpendicular straight down. The way you figure out which one is with the right-hand rule. And it says this. I'm trying to figure out if my video is mirrored. I take, let's say, I need 2 different colors. Let's say this is vector A pointing in this direction. I don't know how well this is going to work. But what I always do is I take the first vector, I curl it into the second vector with my fingers. My thumb points in the direction of the cross product. So if you can imagine here, taking vector A with your fingers and curling it into vector B, your thumb is going to point straight up. that is the direction of the cross product. Or if you look over here, here's the same two vectors. So if I imagine with my right hand taking vector A and curling it into vector B, my thumb points straight up. That is the direction of the cross product of A cross B in this particular case. On the other hand, if I wanted to curl B into A, so now I take my right hand and I curl my fingers from B into A, now my thumb points straight down. That would be the direction of B cross A. So here's the right hand rule that I think is most easy to use, is with fingers of right hand, curl the first vector into the second. So curl A into B. Your thumb points in the direction of A cross B. So let me open up a new tab and kind of do this a slightly different way. So draw view, let's line rules, bam. So one, how do you represent a vector that's coming out of the page or into the page? You know, if I want to have something going to the right, I can obviously draw vector A to the right, and let's just say vector B points straight up. If I were to take A and curl it into B, my thumb would be pointing out of the page. How do I indicate a vector that's going out of the page or into the page? Well, the way we do it is either with a dot in a circle or an X in a circle. This would be a vector coming out of page. And with the X, this would be a vector going into the page. And the way they tell you to imagine is if I shot an arrow. If the arrow was coming towards you, you would see the point of the arrow. And if the arrow was going away from you, you would see the sort of the crosshairs of the back of the arrow. So like in this case, if I were to take A cross B, the direction would be out of the page. So in this case, the direction, if I took my fingers and I curled A into B, my thumb is pointing towards me out of the page. That's the direction of the cross product of A and B. If instead I did B cross A, in this case, if I take B and I curl it into A, my thumb would be pointing into the page. So the direction is into the page in this case. So a couple questions for you. Let's say that I had, let's say vector A, how should I do this? Let's say vector A points straight down. And then vector B was coming into us. So if I had vector A pointing straight down and vector B was pointing towards you, and I took my right hand and I curled A into B, what direction would my fingers point? Take just 30 seconds. Vector A points straight down. Vector B is pointing towards you. If you took A cross B, so I curled A into B, what is the direction? And I don't know the best way of doing this, but so I don't know if this works for you, but B is coming towards me, A points straight down. With the fingers of my right hand, I take the first vector and I curl it into the second vector. So B is coming towards me, A is straight down. With my right hand, I curl A into B. In this case, my finger, my thumb is pointing to the right. So in this particular example, A cross B would point to the right. So I'm sorry. I was looking at, oh, did I ask? Oh, sorry. I was doing B cross A when I was just doing that example. So A points straight down, B is coming towards me. If I take A and with my right hand curl A into B, my thumb then points to the left. So A cross B, the direction would be to the left for A cross B. And then for B cross A, the direction B cross A, the direction would be to the right. So let me pause that just for 1 second and see if there are questions I can answer. So 2 big things. So lab 9, I'm gonna have due, I think next Wednesday. Was the lab you did last week, lab 9? I'm totally spacing. Let me just look real quick. Lab, online resources. Lab, oh yeah, so lab 9 is the one we just did. So yeah, lab 9 will be due next Wednesday. And it's just gonna be uploaded to Mastering Physics. Okay, so let me pause. Questions on just the direction of the cross product. I haven't gotten to sort of the big, long, ugly form with matrices yet, but dot product is a scalar. The end result is a number plus units. The cross product or vector product is a vector, which means it has a direction associated with it. We determine the direction by using the right hand rule. And for that, you take your fingers of your right hand, curl the first vector into the second vector. Your thumb points in the direction of the cross product of A cross B. Okay, if there are no questions, I'm gonna keep going forward, and I wanna talk about just the cross product of 2 unit vectors.
Hey, Joe, could you explain one more time how you got for the direction for B cross A?
For the example we just did?
Yeah.
Okay. So in this particular case, B is coming towards you. A is pointing straight down. So if I have a vector, and keep in mind also, anytime you're looking at like the angles between vectors, you're always drawing them tail to tail. So if B is coming towards me, and then A is straight down, and I take B and I curl it into A. So I'm taking this vector and curling it into the second vector, then my thumb in this case points to the right. That's the direction of the cross product. If I take A cross B, so A was straight down, B was coming towards me, it's kind of weird to do, but I gotta take the first vector, in this case A, curl it into the second vector, now my thumb would point to the left. So thinking about chat here, I can't see the hands. Oh, because of my thing. All right, hold on 1 second. I was wondering about that. Let me do virtual background. How do I do none? I don't want to mirror my image. I have a choose virtual background. How do I turn it off? General. Okay, apparently I cannot figure out how to turn the virtual background off right now. Oh, maybe it's because I'm sharing. Stop share. Virtual background. Damn. Anyway, I can't seem to figure out how to turn it off. Click none. It's not giving me that option. Meeting, blah, 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 blah. Oh, can I do it from here? New video, choose virtual background, none. Oh, none. There we go. Okay. So going back, and let me share this screen again. Oh, it's so sad to see the Millennium Falcon go away. So if A points straight down and B is coming towards me, in the first case, if I do A cross B, I need to take vector A, curl it into vector B with my right hand. My thumb is pointing to the left, hopefully for you guys also. That's the direction of A cross B. If I do B cross A, I'm taking B and curling it into A with my right hand. my thumb points in the direction of the cross product, which in this case would be to the right. The other way of thinking about it, again, let's go to this diagram right here. The direction of the cross product is always perpendicular to the plane that contains both vectors. So if I look over here at this example with A and B in the direction shown, the cross product has to be perpendicular to the plane containing both. So it's either straight up or straight down. In this case, if you can imagine with your right hand taking A and curling it into B, then my thumb would point straight up. That's the direction of the cross product. So what's useful is to think about this in terms of unit vectors. So one, let me kind of do this on this section again before I go over here. Remember, what is a unit vector? Are I, J, and K. Keep in mind, these are dimensionless, which means they have no units. And these have a length of 1. So quick question then, what would then be I cross I, J cross J, and K cross K? Well, if you remember, a dot product of any unit vector dotted with itself ended up giving me 1. Why? Because it's the magnitude of both vectors times the cosine of the angle between them. So I had basically 1 times the cosine of 0. But for a cross product or vector product, the magnitude is given by the magnitude of each vector, which for any unit vector will be 1, times the sine of the angle between them. And the angle between any vector in itself is just 0 degrees. Sine of 0 degrees is 0. So any unit vector crossed with itself, the end result is 0 for that cross product. Now, any unit vector dotted with another unit vector, so I dot J, J dot K, K dot I, and so on, just in terms of the magnitude. We're not looking at the direction. But any unit vector crossed with itself, because the angle between a vector and itself is 0 degrees and sine of 0 is 0, cross product is 0. For any unit vector crossed into another one, again, the magnitude of any unit vector is 1, and the angle between any unit vector and another unit vector is 90 degrees. Sine of 90 is 1, so any unit vector crossed with another unit vector, the magnitude of it is 1. We just need to figure out the direction. So I want to give you a couple examples here. Let's say that my x-axis points to the right, so that's my I. My y-axis points straight up, so that's my J. And then my z-axis, is coming out of the board. So there's my K. You know, you could draw that how you want, but x-axis is to the right, y-axis is straight up, z-axis is coming out of the board. If that's the case, what is I cross J equal to? What is J cross K equal to? And what is K cross I equal to? Take about 30 seconds. Again, the magnitude of any unit vector crossed with itself is 1. I'm sorry, crossed with itself is 0. The magnitude of any unit vector crossed with a different unit vector is 1, but we just need to figure out what are the directions. So, like in this case, let me do this in a different color. If I were to, with my right hand, curl X into Y, or curl A into B, my thumb would point straight out, which is in the positive Z direction or the K direction. So whoa, what's going on here? I cross J ends up being equal to, ends up being equal to K. If I take J cross K, so J points straight up, K is out of the board. If I took J cross K, that would end up giving me I. And then K cross I. If I could imagine the vector coming out of the board, I'm curling it into the x-axis. My thumb would point straight up. So K cross I is equal to J. And then you could do the exact same thing anytime. Let me just put this up here. A cross B is going to have to always end up being equal to negative B cross A. Meaning the magnitude of A cross B is the same as the magnitude of B cross A, but the directions are going to be different. So if I cross J is K, J cross I, oops, J cross I is negative K. K cross J is negative I, and I cross K is equal to negative J. So there's a nice little formula for remembering this. I don't know if they gave this in math, but super useful. I'm gonna have to modify this, and it's this. Let me draw a circle where here's I, here's J, and here's K. And my circle is going to go clockwise. So this is really just summarizing everything above. Anytime I'm going in the same direction as the arrows, I end up with a positive, meaning I cross J is a positive K, J cross K is a positive I, K cross I is a positive J. That's sort of all of this right here. Anytime I'm going in the opposite direction of the arrows, it's a minus sign. So J cross I is negative K, I cross K is negative J, and then K cross J is negative I. It's just a nice shorthand way of remembering how the unit vectors go. So any unit vector crossed with itself, I cross I, J cross J, K cross K equals 0. Any unit vector crossed with another unit vector, the magnitude is 1. And then to figure out the direction, you can just use this nice little circle. If I'm going in the same direction as the circle, I get a positive. So I cross J is positive K, J cross K is positive I, and so on. Anytime I'm going in the opposite direction, it's negative. So let me pause that for a second. Is it okay to use matrices? So what I'm about to do now is show you how you get the cross product of two vectors using matrices. So in order to do that, we are first going to have to learn a tiny bit of matrices. And view. So one, if you haven't had matrices yet, don't worry about it. I'm going to give you just what's called the determinant of a matrix, but we're going to use this just as a shorthand way of figuring out what the cross product is of two different vectors. So one, before I even do that, let's write out these vectors. Let's say vector A was equal to AXI plus AYJ plus AZK. And vector B was equal to, oh, I'm not sharing. Thank you. Okay, sorry about that. So we're going to look at if I have two vectors where I'm given the I, J, and K components of each, and I want to know what is the cross product. Oh, let me get rid of that. So vector A is just AXI plus AYJ plus AZK. Vector B is BXI plus BYJ plus BZK. And I want to do the cross product of A cross B. If you remember, we did a similar thing when looking at the dot product. You end up with 9 different terms. And for the dot product, all but 3 of those terms dropped out. So in this case, what I'm going to do is I'm going to take AXI and dot it into all 3 of these, AYJ, dot it into all 3 of the B's, AZK. So what I'm going to get with is AX, BX, I cross I, plus AX, BY, I cross J, plus AX, BZ, I cross K. So that just was from this first term, AXI, dotted into all 3 terms for Y. Now I can do the same thing, AYJ, dotted into all 3 of these, and I get AY, BX times J cross I, plus AY, BY times J cross J, plus AY, BZ, J cross K. And then last but not least, if I take AZK and cross it into all 3 terms of B, I get AZ times BX times K cross I, plus AZ BY times K cross J, plus AZ BZ K cross K. So I have 9 different terms. And again, same exact thing we did the dot product, except instead of I cross I, it was I dot I. Instead of I cross J, it was I dot J. If you remember, in the dot product, anything that wasn't a unit vector dotted with itself disappeared. Well, in the cross product, any unit vector crossed with itself is 0, which means this term AX, BX, I cross I, this is 0 because I cross I is 0. J cross J is 0, so this term is 0. K cross K is 0, so this term is 0. So I have 6 terms that survive. And if I want to know the direction, again, if I think about this I, J, K, if I'm going in the same direction of the arrows, I end up with a positive. If I'm going in the opposite direction, I end up with a negative. So I cross J is K. So this I cross J is K. I cross K is negative J. Over here, J cross I, I'm going in the opposite direction of the arrows. This is a negative K. J cross K, I'm going in the same direction of the arrows. This is an I. K cross I, I'm going in the same direction of the arrows. This is J. And then K cross J, I'm going in the opposite directions. This is negative I. So we're going to sort of summarize all of these terms. But the way you do this is I took AXI and I crossed it into all 3 components of B. I took AYJ, crossed it into all 3 components of B. I took AZK, crossed it into all 3 components of B. 3 of those components are 0. 3 of those terms are 0 because I cross I, J cross J, K cross K is 0. So then if I look at the remaining terms, what we're going to get is a big, ugly expression for the cross product. So let's summarize these. So let's look at the I terms. I have AY, BZ times I and AZ, BY times negative I. So I'm going to write this as AX, where am I? AY, BZ minus AZ, wait, what did I do? I, K cross J is negative I. Oh, AY, BZ minus AZ, BY. This is in the I direction. And then if I look at the J's, I've got AZ, BX, so plus AZ, BX, and then I have a minus AX, BZ. minus AX BZ in the J direction. And then plus, for my Ks, I've got an AX BY. And then I've got an AY BX in the negative K, so minus AY BX K. This is the sort of ugly expression that you get for the cross product. Now, given that I'm not asking you to memorize anything, you could always just copy this down and then plug and chug. But you're going to be doing cross products a lot in Physics 4B. If you continue on to circuits and things like that, there's many, many cases where you're looking at a cross product. The easiest way to do it is using matrices. And so there's an easy way of just getting this result using matrices without having to memorize it or do anything like that. So before I can do that, I need to just tell you a little bit about matrices. Let me think. Do I need to tell you really about matrices or just give you the formula? Let me just give you the formula. I hate doing this, but if you take linear algebra, you will basically have an entire semester of matrices. But for now, just think of this as a little formula. If I have a 2x2 matrix where I just have 4 numbers, so this could be a matrix that's just like 3, 4, 1, 5. The way we define the determinant of a 2x2 matrix is basically it's the product of AD minus the product of BC. So it's just AD minus BC. Again, I know you may not know what matrices are, and for this particular course, it's not super important. But so if I had a matrix like this where I had 3, 4, 1, 5, the determinant would be 3 times 5 minus 4 times 1. I get 15 minus 4. This would be 11. That's how you do a 2x2 matrix. So it's just a really simple formula. It's the top left thing times the bottom right minus the top right times the bottom left. That's a 2x2. Well, if I have a 3x3, so I'm going to write this as A, B, C, D, E, F, G, H, I. The way you do a determinant of a 3x3 matrix is you create 3, well, here's the formula, is you take this first column here in A, and you get rid of the row in the column that A is in, and then you're left with the 2x2 matrix here, E, F, H, I. So what it is it's A times the 2x2 matrix of E, F, H, I. Then, and here's a case I'm just going to tell you that this second one, there's a minus. Then I go to this next row, and I get B. And I get rid of the row in the column that B is in. And what I'm left with is D, F, G, I. So this would be times D, F, G, I. And then I get rid of the row and column that C is in. So I get rid of this part down here. I'm left with D, E, G, H. So plus C times D, E, G, H. And then the end result is just like before. So this would be A times EI minus FH minus B times DI minus FG plus C times DH minus EG. So I'm going to show you how you can use this to quickly get the cross product. So again, a determinant is almost like an absolute value of a matrix. It's a very simple formula. A 2 by 2 determinant is I take A multiplied by D, subtract B multiplied by C. If I have a 3 by 3 matrix, I basically get the determinant by turning it into, in a sense, 2 by 2 matrices and multiplying them together with some constants out in front. So here, what I do is I'm basically going across this first row. I take A, and then I'm going to multiply it by a 2 by 2 matrix that results when I get rid of the row and column that A is in. So I don't consider this DG, BC. The 2 by 2 matrix that I'm left with is right here for A. Then I have B. For reasons I'm not going to go into, you have a minus sign there. And then I get rid of the row and column. Let me just do this over here again. Actually, cross product. Okay. So here's this little memorization aid. So again, if I had a 3 by 3 matrix here, and I have, and let me just give you a little preview. How we're going to figure out the cross product is across the top, you write IJK. Second, you have the X, Y, and Z components of the first vector. Third one, you have the X, Y, and Z components of the second vector. And then this just becomes a determinant of a 3 by 3 matrix. So what I do is I take the first one, which in this case is I, and then I get rid of the row and column that I is in, and I'm left with a 2 by 2 matrix of AY, AZ, BY, BZ. And that's what this is showing up here. Instead of AX, AY, AZ, they're just writing it as 1, 2, 3. Instead of BX, BY, BZ, they're just writing it as 4, 5, 6. So here's my I get rid of the row and column that it's in, and I'm left with this 2 by 2 of AX, AZ, BX, BZ. Now for the second one, there's a minus sign. And again, if you have linear algebra, you'll go into Y. And then I get rid of the row and column that J is in, and I'm left with AX, AZ, BX, BZ. So this is AX, AZ, BX, BZ. And then I have the third one, K, and I'm getting rid of the row and column K is in, and I'm left with AX, AY, BX, BY. So this is times AX, AY, BX, BY. And then just using that formula, what I get is, I would have I times AY, BZ, minus AZ, BY, minus J times AX, BZ, minus AZ, BX, and then plus K times AX, BY, minus AY, BX. This is the result of the cross product of two vectors. It's exactly the same as what I have over here, except instead of plus, I end up writing this as minus J times, as you'll see here, we go back, minus J times AXBZ and so on. It's exactly the same thing. So here's the end result is, if you wanted to just memorize a formula, which I don't recommend, it's this. But the way you get it is by drawing basically a 3 by 3 matrix where I have IJK across the first column, first row, and then AX, AY, AZ, BX, BY, BZ, and then just using this little formula I gave you for determining the determinant of a matrix. Booyah! Let me stop that for a second. I didn't really want to see go through this for 45 minutes. But even if I don't have a ton of problems using the cross product this way, like I said, in 4B, I'm trying to think about, as I'm finishing off Physics 4A, what do you really need to know to move on to 4B and 4C? So I'm going to cut out some stuff from Chapter 12 I know is not going to be directly applicable, but determining the cross product is something you will need to do in Physics 4B and a little bit in Physics 12, well, Physics 12, Chapter 12. So let me pause. Questions I can answer about the cross product. What questions can I answer? There's no questions. I want to just give you a quick little preview of Chapter 12. Spend about 5 minutes, and then we'll sort of end the lecture portion, open up office hours. So questions? Okay, let me just share the screen one more time. So everything up until now has been sort of translational motion, where you have an object which is sort of physically moving through space from one position to another. Now in Chapter 12, we're going to start looking at rotational motion. So rather than looking at something sort of moving in some sort of curved path, we're going to be looking at basically rigid objects which are rotating. And a rigid object is an object that can't change its shape. So most spinning objects, a wheel, a ball rolling, we could consider to be rigid objects. Something that's not rigid might be like the sun. I don't know if you know this, but as the sun rotates, all parts of the sun are not rotating at the exact same speed. The inner part of the sun is rotating at a slightly different speed than the outer part of the sun. It's not considered a rigid body. In a rigid body, all parts are rotating at the exact same rate. The object is not changing its shape at all. So initially, we're going to look at an object which is rotating about a fixed axis. So like a pulley spinning. Then we're going to start looking at rolling motion. And a rolling motion is interesting because I think I previewed this, but a rolling object has a form of kinetic energy in addition to the 1/2 mv squared because the entire object is moving. It's also rotating, and it has what's called rotational kinetic energy. And so every physical quantity that we've studied so far, it has a linear thing like position, velocity, acceleration, force, also has a corresponding angular quantity. So we started off dealing with linear motion, looking at position, velocity, and acceleration, defining how those were defined, positive and negative, and so on. Our rotational quantities are all going to be very similar. Instead of position, we're going to measure angular position in radians. And I'll remind you what a radian is probably on Monday. Angular velocity is going to be how quickly something is changing its angle. So for example, if I have let's say a record, and this is a weird shaped record, but this record rotates, and so this thing goes from here to here. It rotates through some angle. Well, I could have something rotating either very slowly or very rapidly. Angular velocity is really just how quickly something is rotating. We measure it in radians per second. And then angular acceleration is how quickly the angular velocity is changing. So for example, if you guys remember the old record players, initially they're not moving, and then you turn it on and it goes from some angular velocity of 0, and then it increases up to some, angular velocity 45 revolutions per minute or whatever. Angular acceleration tells me the rate at which my angular velocity is changing. A couple other just previews in terms of quantities we've seen before. Like I said, pretty much every linear thing that we had has a corresponding angular quantity. So like instead of the sum of the forces equals ma, forces in terms of angular quantities, we start looking at what's called torque. And a torque, in essence, is like a turning force. It causes an object to rotate. So instead of the sum of the forces, we're going to have the sum of the torques. And just as a little preview, the reason why cross product is important is because the torque on an object is defined as R cross F, or RF sine theta. And just to give you an idea what this is, let's say I have a door, and I want this door to rotate, and I apply a force to it. Well, how likely that force is going to be to cause this door to rotate is going to depend upon a couple things. One is the force. Two, how far away the force is applied. So here, R is the distance between where the force is applied and the axis of rotation. You can kind of see from this, if I have a bigger R, I'm going to get more torque for the same force. So like here, it's going to be more effective for me to try and open a door if I exert a force farther away from the axis of rotation. You may never have thought about this, but this is why they put a doorknob where they do. I mean, could I put a doorknob right here? Sure, but what ends up happening is this distance away from the axis of rotation is much smaller, so I would have to exert a much bigger force to have the same torque as if the doorknob was real far away. A couple other things. God darn it, I'm gonna get rid of that. Instead of mass, we're gonna be dealing with something what's called the moment of inertia. And that depends upon how the mass of an object is distributed. The more mass farther away from the axis of rotation, the more rotational inertia it has, the harder it is to cause it to turn. And again, instead of acceleration, we have angular acceleration. A couple other things, just so I'm on it. Kinetic energy, 1/2 mv squared. We're going to have a rotational kinetic energy term, which is 1/2 I omega squared. The angular equivalent of mass is this moment of inertia. The angular equivalent of speed is angular speed. And so really every quantity we've had so far, every equation has an angular equation. I don't know how much time I'll spend on these, but even the equations of constant acceleration that we've seen before. Vx equals v naught x plus axt and so on. Every single one has a corresponding angular equation. So instead of Vx equals V naught x plus axt, we have omega equals omega naught plus alpha t and so on. So that is it in terms of the cross product and the introduction. Is this note posted on your website? Yes, actually, let's take a look because I don't remember. I've done so many things online. Physics, so this is your online resources page. Hey, look at me, I did. So rotations of a rigid body, I do have the OneNote posted. And again, I'm only going to post the PDFs once I'm done because I have to convert the entire thing into a PDF. Okay, let me just open it up for questions I can answer. Okay. Let me just throw this out there as a quick little preview. There are 3 weeks left in class. So in terms of labs, we're going to do something interesting. I will sort of present the lab to you tomorrow. But what you're going to do, in essence, is you're going to have 2 weeks to do your own at-home physics project using stuff you have from home and looking at some physics principle that we've seen so far. And I'll talk a little bit more about this, but things like rubber bands and looking at, does a force of a rubber band obey Hooke's law, or conservation of energy. And this is going to be kind of fun and interesting because we're not going to have force sensors. You're not going to have meter sticks and things like that. So rather than measuring, let's say, force in newtons, you're going to have to create your own homemade units. So for example, if I was doing this, I have like 30 pounds of Legos. I would start measuring force and how many Legos a rubber band could hold or something like that. And then I could use that to start looking at vector equations and things like that. So I'm going to throw this out there. John and I are going to be talking about this weekend and then presenting something on Wednesday. But there will be no like formal lab this Wednesday where I'm going to record something. I'll record a video giving you some information, but basically you're going to have 2 weeks by yourself or with 2 or 3 other people to come up with some sort of, I don't want to call it science fair because that sort of has certain connotations, but an at-home physics experiment designed by you using everyday equipment like rubber bands, or most pens have a spring in them. You could grab that spring and try and do some sort of calculations with it. So I'll give you some more information, but I want to throw that out there now for you to start to let that percolate. I am not designing any more labs. This coming Wednesday, I'm going to talk about the labs that you're going to be designing yourself. And then in essence, you have 2 weeks to do it. And the very last Wednesday of the semester, you're basically going to do a little 5-10 minute presentation of what you did, presenting your data and things like that. I think it kind of sounds like a fun way of yeah, having you do some sort of fun physics experiment at home, designing it yourself. Okay, I'm officially ending lecture portion. Office hours, questions that I can answer. I'm going to be here for 20 minutes. Anything you have about anything. If not, thank you all for those of you who joined me on Zoom live. I'm going to stick around for 20 minutes. Let me know if you have any questions.
Hey, Joe.
Yes.
I have a question. When are we going to be able to see what we got wrong on the celebration?
I believe you should be able to see it now. Once it's due, then I believe you can at least get your grade. And
I can see my grade, but I can't see, like, I would like to go back and look at the problems that I got wrong, if possible.
Okay, that might be a setting that I'll look into that.
Okay,
Probably won't get a chance to do that today, but I have it set up so that you can see your score once it's done, but maybe since it's a test, you may not be able to see exactly which ones you got wrong. I'll look into that.
Okay, thank you.
And just so you know, I will post, when I post this lecture, I will post the solutions to the celebration.
Okay, thank you.
So at a very minimum, you'll have the solutions, but I'm hoping that everyone can you access your old quizzes and see what you got wrong?
We can't see the answers we input, but we can see what the right answer is.
Huh, okay, I will look into that and see if that's some kind of setting that I can change as the instructor.
Okay, thank you.
But that's probably not gonna happen until tomorrow, just to let you know.
Okay, that's fine, thanks.
You're welcome. Anybody else? Darian, you got a question or anybody? Boop, boop, boop. From Christopher, I cannot hear you. I already bound the celebration compared to my grade. Is there any way to get my grade up? I'm going to calculate everybody's grades, hopefully next week, send them out. I'm thinking most people are doing well, and like I said, the A to B, I'm going to sort of be a bit generous. So I don't think I'm going to be able to do any extra credit, but once I give out all the grades, if you have questions, let me know and we can talk about specifics. Yeah, Christopher, it says that you're not muted, but I don't hear anything coming from you. Thank you, everybody. So yeah, I'm gonna just hang out here for 15 minutes. Let me know if you have any questions. If nobody does, I'm going to just sort of mute the video. Just so
Can you hear me now?
I can hear you now.
Yeah, I was just kind of wondering if you could look at like I don't know, I think my grades kind of plummeted.
Oh, I don't have anything in terms of anybody's individual grades. So I'm going to, at some point in the next few days, download everything off of Mastering Physics, get as much as I can graded, but my goal is to give everybody their grades within a week.
And then the other thing I was wondering about was like, I know it says like some of the homework that I did has like a really low score, and I'm not